Yeah, okay, guys, let us start then. Okay. So, my audio and my video both are clear, right? Just once confirm me, we'll start. My audio and the screen both are visible. Okay. Okay, then, fine. See, before going into strain, let me just give you the basic classification of stresses. I'm not going to go in detail about this. Just I will give you a basic classification, because if you see stresses, there are many classification which you will be seeing further. Okay, for example, if I take stresses, the basic classification is something like normal stress and shear stress. Okay, shear stress, or you can also call it as tangential. Okay, tangential or shear. This normal is nothing but, this normal stress has different classification. One is axial. Okay, of course, this normal is also otherwise is called as axial. And bending stress is also an axial type. Okay, bending stress is also a normal type. Okay, so these things I will be discussing it separately in the separate chapter, so I'm not going into deep about it. But of course, yes, normal stress means there are different types. One is normally axial loading and another one is bending, and bending is also a type of axial loading. Okay, and shear stress means we can classify it into two. One is direct shear stress and another one is torsional shear stress. Don't worry, don't write also all these things, I will be giving you later. We will just understand what is mean by this normal and this shear stress properly. Normal is nothing if the load acts perpendicular to, okay, load acts perpendicular to the cross section. That is why the word normal indicates. Okay, if the load acts perpendicular to the cross section, then it is called as this load by area is called as normal stress. Okay. And normal stress can be classified into two, basically a general classification based on the sign. One is tensile. Okay, if the load tries to elongate, okay, if the load tries to elongate the member, then it is tensile. And if the load is trying to contract, okay, if the load is trying to contract the member, then it is compressive load. Okay, so if it is trying to contract it, it is compressive. If it try to elongate, it is tensile. And now if you talk about shear stress, okay, if I talk about shear stress, it's something like, let me take one example. Okay, sorry, let me change the color. Actually, this is not at all good. Let me take one example. Consider that I'm taking a member like this. Imagine that it is a three-dimension member. What I mean three-dimension means it's having a dimension like this also, but I'm not going to show it. I will just show you this time and then I will erase it. Okay, so it has some width. Okay, it has some width also. Okay, it has some width also, and some thickness and some length. Okay, right, so but I'm not going to show this. Okay, and consider that there was a small wedge. Okay, small wedge here at the top. Okay, small wedge, okay, at the top, and similarly there was one more wedge at the bottom. Like you can say that wedge is nothing but a small again, if I want to show it in 3 dimension, it is something like this. Okay, I hope you could understand this, but it's not that easy to draw 3 dimension and to represent it 2 dimension. It will be easy. Something like this. Okay, something like this. Okay, there is a wedge. Okay, right, so I will just show you the 2 dimension figure. Now let us assume there are two forces which is acting. One is load P here, and there was another load P here. And now what is mean by this shear stress? See, shear stresses are nothing but, if I am going to cut this section into two. Okay, let us take this is section, this is part 1 and this is part 2, and if I represent part 2 here, okay, it will look something like this, right? It will look something like this. Here, a force of P is acting downwards, and this is the cross section. Okay, this is the cross section. This is the cross section. If you could see that, it's in somewhat. I could draw it in a 3-dimension. Okay. So this is the cross section. Let me take the cross section area be A. Now there is a force P which is applying in transverse direction. Okay, force P is acting in transverse direction, and due to this force, due to this externally applied force, there is going to be some internal resistance which is created on this cross section. Okay, due to this externally applied force, there is going to be some internal resistance which is created on this cross section. And what will be the direction of that internal resistance? Very simple. We know that it has to be in static equilibrium. It has to be in static equilibrium means summation of forces has to be 0. What are the total forces which is acting? One is force P, another one is the force which is acting on this section. Right? One is force P, another one is the force which is acting. That is the internal resistive force which is acting on this section. Okay, a load P is acting downward, and due to this load there is going to be some internally resistive force which is created on this cross section, and this load is acting downward, right? This load is acting downward, so obviously this load should act upward, then only summation of F will be 0, right? Which means P, let us take this is V. Okay, P minus V is equal to 0, which implies P is equal to V. That is total force which is acting downward equals to total force which is acting upward. So the internal resistive force in this case, okay, let us take that internal resistive force be V, okay, which is acting over this cross section A, okay, and it is acting from bottom to top. The applied force was acting from top to bottom. Why they are opposite in direction? Because then only static equilibrium will be balanced. The total internal resistive force should be equal to the total applied force. Okay. Now, this internal resistive force which is acting over this cross section per unit area is nothing but shear stress. And now you could understand what is the difference between shear stress and normal stress. Shear stress is caused due to transverse loading. I'm applying a transverse load. Because of that transverse load, this area is offering some resistance, and that internal resistive force, okay, this is the internal resistive force per unit area is nothing but shear stress. Actually, this shear stress is in fact direct shear stress. Okay, this shear stress is direct shear stress. There is one more shear stress called as torsional shear stress that we will be discussing it separately in torsion chapter. Okay, and see, one thing which I wanted to say, if you take this cross section, okay, if I'm taking any cross section, let the cross section be XX, the shear stress is not going to be same everywhere. What actually we assumed here is the load remains same everywhere, load is same everywhere, so shear stress is also same. But in actual case, okay, some point shear stress will be less and some point shear stress will be more. Okay, some point shear stress will be less and some point shear stress will be more. That is, there will be some variation of stress in this cross section. So this shear stress which I'm finding is not the total shear stress, or it's not the actual shear stress, it is the average value. What does mean by average? I'm taking an average load here. Okay, instead of considering the variation, okay, instead of considering the variation, I'm taking some average value V, and that average value per unit area is nothing but our shear stress, and that is average shear stress. See, don't worry about this average shear stress and actual shear stress. I will be giving you an equation for this actual shear stress in separate chapter. Okay, there is a separate chapter called as shear stresses in beams, and in that chapter I will talk about this more. Okay, right, so what else, and some other examples which I could give here. Okay, some other example, just take a piece of paper, okay, piece of paper, and tear it. Okay, just tear it. When you are trying to tear it, the force or the stress which is acting on this, okay, on the cross section of paper is shear stress only. Okay, the stress which is acting on the cross section of the paper is shear stress. Okay, so keep this in mind. This formula is for average shear stress only. It is not for actual shear stress. Actual shear stress, we will be determining it later in a separate chapter. Okay, so and yeah, that's it. Any doubts here? I am just giving you a small introduction only. I'm not giving more examples. As we proceed, we will see some more examples, so that at least I can start that UTM. I don't know. I'm sure I cannot complete it, but at least I can start that tensile test. Okay, then fine. Let me proceed. Okay, listen. Next, I'm going to discuss about strain. Okay, see, before going to strain, we need to understand what is mean by this deformation. See, deformation means you might think that if there was some change in the length or some change in the distance, I can say it as a deformation. No, no, it is not. Deformation includes deformation includes both change in size, that is nothing but what the change in length or change in volume, sorry, change in length or yes, change in volume, those things. In addition to this, we have to consider change in shape also. What does it mean? I will give you an example. So deformation includes both. Okay, deformation includes both. One is change in size, another one is change in shape. Okay, take an example. Take an example. Just I'm taking a cube, okay, or a cuboid, whatever it is. Okay, so I'm taking a cube here. Okay, so just consider that I'm fixing it in the bottom. Okay, I'm fixing it in the bottom. Bottom side is fixed. I'm applying some shear force. Okay, a transverse force. Okay, from the bottom. As you could see that it's a transverse force. So what will happen if I apply a force something like this? Okay, if I apply a force something like this is going to, I will just show you a two-dimension figure. Okay, it will result in, so initially the front view will look something like this, but after application of this force, okay, it will look, after application of this force, it will look something like this, as you could see here, right? I hope that you understood initially how it looks and finally how it looks. Let me show you in another color. Okay, initially this is how your front view looks, but after application of force F, it's going to look something like this. Okay, so there is going to be some small change in the angle, or you can say that change in the shape. Initially it was, the front view was something like a square, but now it is something like a parallelogram. Okay, so this is what I will be calling it as change in, I will just directly connect it. This is nothing but change in shape. And then what is mean by change in size? That is what we are discussing from the beginning. Okay, and of course this change in shape is occurring due to shear force. Okay, I'm applying some shear only, right? Some transverse force in this direction. Due to that transverse force only, it is getting tilted. Okay, it's getting tilted. Okay. Yeah, what is mean by change in shape then? Simple. If suppose this is the member, and if I apply a force F on it, so what will happen? What will happen? There is going to be, sorry, I don't know. Yeah. So what will happen? There is going to be increase, right? This is how it looks. So I'm applying a force F. Its diameter is increasing and its length is decreasing, and this small change is nothing but a deflection or a deformation, and in this case it is change in size. Okay, so I can call it as to be deformation. Either it is a change in size or change in shape, both are deformation only. And now why it is very important, why it's very important to talk about change in size and change in shape, because by using these two things we are going to classify two different types of strain. And the first strain which I'm going to discuss is normal strain, which is represented with epsilon. So epsilon, that is normal strain, is something which is due to change in size, which means how much the length is changing with respect to its original length. Let me keep it as L only. Okay, so let me keep it as original length of this is L initial, final length is L final. Okay, so change in length means L final minus L initial by original length, this is L initial. Okay, so this is original length. So normal strain, or sometimes it is called as engineering strain also, normal strain or engineering strain. Okay, that is given as how much deflection is happening. Okay, change in the length to that of original length. Okay, and there is one more strain called as shear strain. Okay, shear strain, which is gamma. Okay, I will come for it. Before that, see, in this case, this epsilon will be positive. Okay, will be positive if LF is greater than Li. Okay, when LF will be greater than Li if it is tensile load. Okay, if the load is tensile, then final length is going to be more than that of initial length. Okay, then normal strain will be positive, and epsilon will be negative if LF is less than Li, which implies it is a compressive load. Okay, if it's a compressive load, then epsilon will be negative. If it is a tensile load, epsilon will be positive. Yeah. Before going into next, I just forgot to mention it, the last. Yeah, this I forgot to mention. Stress. Okay, stress will be positive if it is tensile, our sign convention. Okay, and stress will be negative if it is compressive. I forgot to mention, but just remember that tensile will be positive for a stress and also for a strain, and similarly compressive will be negative for stress and also for strain. Okay, and now how to find out shear strain? Simple. See, let me erase it. Okay, let me erase it and I will do it from the beginning. See, shear strain is given as, until now, was there any doubts? True stress, true strain, I will talk about it later. Yeah, I will talk about it later. But for now, it is engineering strain. Okay, it is engineering strain. Right. See, initially, for finding out shear strain, let us take, for finding out shear strain, what you need to do, you have to take two line segment. Okay, understand this properly, how we are going to define shear strain in strength of materials, because there is something called as shear strain rate, which we will be discussing in fluid mechanics. Okay, shear strain rate, which we will be discussing in fluid mechanics, shear strain, which is what we are going to study in strength of materials. These two are different parameters and we will be finding that using different definitions. Okay, so I'm not going to discuss about shear strain rate now, but just try to understand what is mean by this shear strain. Okay, see, for finding out shear strain, you need to take two line segments. Okay, let me take this line segment O A, another line segment OB. Okay, two line segment before deformation. Understand it properly. It's a very good definition. Most of the times you won't able to find it that easily. Yes, this definition was there in R.C. Hibbeler, but I don't think so you will be finding out in any other local author books. Okay, right. So now just listen carefully. Shear strain is nothing but let me first define it, then I will let me first talk about it, then I will be defining it. Okay, right. What you need to do, you take two line segments. Okay, two line segments. I'm going to take OA and OB in this case, and those two line segment has to be perpendicular to each other. Those two line segment has to be perpendicular to each other, and I need to take these two line segment before deformation, which means before application of this load. Okay, before application of the load. Okay, I'm taking this front view. Let me take it as OA B, sorry, this is B, right? OAB, and let it be C. Okay, I'm taking the front view and I'm taking two line segment, which is OA and OB, which is perpendicular to each other. Okay, before deformation. Now, after application of force F, of course, it's going to get deformed. Let me use another color here. So it's going to get deformed, and we know very clearly it's going to deform like, it's going to deform like this. Okay, approximately. So this B point will shift to here let us take it as B dash, okay, and this C point will shift to C dash, okay. So I'm taking two line segments OA and OB, which is initially perpendicular. Now after application of the load, okay, after application of the shear load F, okay, after application of the shear load F, it's getting the, obviously OB is getting tilted by some angle. Let me take that angle to be let me take it to be alpha, okay, and of course this angle will also be alpha, okay, angle between AC and AC dash, and similarly angle between OB and OB dash are alpha, okay. Now see, initially OA and OB was perpendicular to each other, that is 90°, but now after application of this force P, the angle changed and it became something like this, right? So we will take that as theta. This is the new angle, okay, this is the new angle between OA and OB. Now let me define shear strain. Shear strain is nothing but change in the angle, okay. Shear strain is nothing but change in the angle. Understand it properly. Change in the angle between two line segments, which is initially perpendicular. We know that OA and OB are initially perpendicular, initially 90°, but after application of the force, the angle getting changed. And now how much change? Okay, how much change? That change is nothing but shear strain. Any doubts until now? Any doubts until now? Okay, so there are no reply, then no problem, I guess so. Okay, so that change in the angle is called as shear strain. And how to find out that change? Listen carefully. I'm not saying the new angle. The new angle is not shear strain. I'm saying that the change in the angle is shear strain. So what is the change? This is the change. Okay, this is the change. This is not. Okay, theta is the new angle between OA and OB. Alpha is the change, right? So which means shear strain gamma is equal to alpha, which can be also written as, how I can write? See, this angle is 90°, right? This angle is 90°. This is theta. Theta is nothing but new angle between OA and OB. Then alpha will be 90 minus theta, right? 90 minus theta. Okay, but this is wrong. This is wrong. See, my definition is correct. My definition is correct. Even gamma is equal to alpha is also correct. But alpha is equal to 90 minus theta is wrong. Can anyone say why? Can anyone say why? See, my definition is correct. Shear strain is nothing but change in the angle between two line segments which is initially perpendicular. That is correct. And from this figure, we got that change in angle is alpha. Fine. And I'm taking theta is this angle between OA and OB, new angle. So that obviously if I subtract 90 with theta, I have to get alpha, right? But I'm saying that this is wrong. Anyone who can just guess or who can think about it, why it is wrong? It is surely wrong. Why it is wrong? Any ideas? See, it is because of this type of mistake. It is because of this type of mistake. I lost 2 marks, and also I lost some minus 0.66, because we know that 2 marks have negative marks of 0.66, right? So I lost during, when I was writing GATE exam, I lost 2 minus 0.6, that is minus, I lost minus 2.66 marks due to this one mistake which I am going to highlight. See, whatever I am giving you, okay, whatever I am saying you, many times the mistakes which I was saying, it will be like the mistakes which I would have done during my preparation, or any other friends of mine would have done during my preparation. Okay, so and this is a mistake which cost me minus 2.66. Okay, and that mistake is SI unit of angle. SI unit of angle is radian. I did this mistake. Instead of taking it in radian, I substituted it in degree and I got some different answer, but the answer should have been substituted in radian. So this is wrong because SI unit of angle is radian. So the correct way to represent it is pi by 2 minus theta. So unit of shear strain is radian. It might feel like it might seems to be very simple. It will be simple, but surely it will cost you. Like you might think that 2.66 is not that much big mark, but yes, of course it is a big mark. If you are aiming for some IIT or if you are aiming for PSU, that 2.66 is a huge mark. I will just say you some one small behind story. Okay, that 2.66, how it is affected. See, I got something around 68. Okay, and one of my friend got some 70 point something. Okay, some 70 point something. I didn't get MTech in IIT Madras. I didn't get MTech in IIT Madras. I got only MS. Okay. Of course, getting MS is difficult. I will say you another backstory later. Okay, I didn't get MTech. Okay, I got only MS. But this guy got MTech. And the difference in marks, okay, difference in this 2 mark, it is something like 500 ranks. Okay, it's something like 500 rank, which means 500 seats. You are behind 500 seats. There are 499 students or 499 aspirants who are before you who could get the seat and you are not able to get it. Okay, so initially I didn't get MTech, I got MS. But the fun fact is this guy has also applied for MS. Okay, this guy has also applied for MS, but he didn't get MS because for MS we need 4 things. Okay, one is CGPA, another one is gate score. Okay, gate score has to be moderate. Moderate means at least 60 plus will be very good. Okay, CGPA is something like 7.5 plus. Okay, these 2 things are base. These 2 things will be useful only for getting an interview call. But once you got an interview call, there will be written test in IIT itself again. Okay, again there will be one written test, and again there will be one interview. So if you pass this 2, they will be giving you MS seat for you. But MTech is not like that. MTech depends only on gate score. If you get 75 plus, then surely you will get MTech in very good college. In IIT Bombay, IIT Madras, or IISc Bombay. Sorry, IISc Bangalore. So it depends only on gate score, but MS depends on CGPA, it depends on written test, it depends on interview. So there are some other performance which is required from our side. But MTech required only gate score. So because of this 2 mark, I didn't get MTech, I got MS. I hope that you would have understood why I'm saying that each and every mark is important. 2 marks will give you some 500 rank leap. Okay, so just 0.5 mark will give you some 100 rank leap. 100 rank means you have to think with respect to seats. It's like 100 seats. 100 seats in IIT. Huh. Okay. So I just went into somewhere else. Understand the importance of each and every mark in gate exam. It's not like that you will study something and you will go and I will secure some good rank. Not possible. Your complete dedication is very important. You have to be very cautious when you're writing exam. These types of mistakes, silly mistakes, are possible. Okay, and as I said that this is one of the silly mistake which I did, which costed me 2.66. But I did many other silly mistakes also. I'm not ready to say all these things now, but I will be saying it whenever the time comes. I will say. Okay, right. So gamma is equal to alpha, which is equal to pi by 2 minus theta. So shear strain angle is radian. Remember this. Angles SI unit is radian. Okay, so whenever you are substituting angle separately, something like, for example, e to the power of mu theta. Okay, here angle should be in radian only, compulsory. Never substitute it in degree. Or something like this, pi by 2 minus theta, or y is equal to theta into 2. Something like this. The theta should be always in radian. Okay, but you are having like this, y is equal to sine theta. Okay, trigonometric quantities, even if you substitute in radian or even if you substitute in degree, your answer is not going to vary, because sine pi by 2 or sine 90 degree, both of them are going to be same only, both of them are 1 only. Okay, similarly sine pi by 3 or sine 60, both of them are going to be same only. Okay, so if you are substituting in trigonometric quantities, no issues. But if angle appears individually like this, e power mu theta, theta into 2 or 5 theta into x or something like this, then you need to substitute theta only in radian. A very important silly mistake. Okay, mark it down. If you are not taking care of it, then surely you will also lose some marks because of this. Okay. Okay, so shear strain is radian, fine, well and good. Unit is radian. Now, what about normal strain unit? I forgot to say. Change in length, right? Change in length is obviously mm or meter, and this length is also mm or meter. So mm and mm, it's going to be no unit. Okay, no unit, or you can say that mm per mm. Okay, and there is some range which you can keep it in mind. Okay, so this normal strain will generally occur between 0.001 to 0.25. Okay, I'm just giving you a general range. General range, you remember this, it might be useful somewhere. Okay, why I'm asking you to remember the range? For example, again, this is also a trick or a tips when you are writing exam. Suppose you are solving a problem. You are solving a problem and you are getting strain as some 3.2. Okay, you're getting strain as 3.2, then I'm damn sure that your answer is wrong, because your answer has to be in some point value. Okay, 0.001 or 0.25 or zero point 0.3, something like that. There is no possibility for 3.2 or 5.2 or 6.2. Okay, so this is wrong. So by seeing your answer, you can identify, yes, I did some mistake. I did some calculation mistake. I need to go back. I need to correct it. That can be identified. So try to remember the range. And one more thing, this strain is there, right? Normal strain. We have another one unit also. We can represent it in percentage. Okay, if you represent in percentage, of course it will be like 1%, 2%, 3%, something like that. We can represent it in percentage also. Okay, sometimes we will be representing in percentage, but the most familiar unit is no unit. That is mm per mm or no unit. Okay, most common unit. That is done. I hope that. Okay. Any doubts until now? Any doubts until now? Any doubts until now? Okay. Okay then. What I was saying. Right. See, there is something called as prismatic bar. Okay, just remember this. Prismatic bar means the diameter will remain same, or else I can say that not even diameter. I can say that cross section. Okay, if I take a member whose length is L, okay, the cross section will remain same. If the cross section remains same, then I can say that it's a prismatic bar. Cross section means it can be diameter or it can be length into breadth. That is, it depends on what type of cross section it is. Okay, but um, most of the times we will be dealing with circular cross section only. Okay, and one more thing. Suppose if you are taking a member like this and I'm applying a load. Okay, due to this load, there will be elongation, right? There will be elongation like this. The elongation happens in this direction. Okay, delta and change in length will happen in this direction. So strain which is happening in longitudinal direction. Okay, strain which is happening in longitudinal direction is called as longitudinal strain, and it is given as change in length to that of original length. Let the original length be L. Okay, see, if longitudinal direction is extending, okay, if in longitudinal direction if it is extending, then diameter is decreasing. Let the initial diameter be d1 and now the final diameter is d2, so change in diameter will be equal to d2 minus d1. Okay, that is, it will be negative, it is decreasing. Okay, diameter is decreasing. So if I apply a longitudinal load, In addition to strain in longitudinal direction, strain will also be there in diametrical direction or lateral direction. Okay, so lateral direction, that is nothing but lateral strain or transverse strain. Okay, this I will write it as longitudinal. Okay, lateral strain or longitudinal, lateral strain or transverse strain, that is equal to change in that diameter with respect to original diameter. Okay, so let the original diameter be DO. Okay, this is length LO, this is length LO, DO be the original diameter. Okay, so change in diameter by original diameter is the lateral strain. Okay, and it's pretty obvious that if this longitudinal strain was positive, then lateral strain will be negative. If longitudinal strain is negative, then lateral strain will be positive. They will be opposite. That is, if it is extending, if length increases, then diameter will decrease. If length, just a second. So if length increases, then automatically diameter will decrease, and similarly, if diameter increases, length will decrease. This is some simple things, right? So I'm not going into deep about it. So that is all about the introduction of strains and longitudinal, lateral strain, all these things. Let me proceed for UTM. If there was any doubts, you just comment it. I will check. Okay. So let me proceed for UTM. You can comment it if you have any doubts. I'm just drawing it roughly. I'm not able to draw. Let it be. I will just draw it roughly. Okay. Okay. So this is the specimen. Okay. This is the specimen. Okay. Somewhat. And let us consider this is our specimen. Okay. Okay. Right. So listen. Let us discuss about tensile test. Okay, that is tensile test will be done in universal testing machine, that is UTM. Okay, so let us consider that this is our UTM just for consideration. It is not that good. Okay, so let us take this is our specimen. Okay, this is our specimen. I'm going to take a mild steel specimen, that is a ferrous material. Okay, so a mild steel specimen, and generally we will be fixing 2 points. Okay, first of all, why we are doing this tensile test? We are doing this tensile test to find out different points at which failure occurs. Okay, or I can say that for finding out a different property of the material. Okay, by doing this tensile test, we will be finding out various properties of that particular material. For example, if I'm taking mild steel and if I'm doing UTM, I will be finding out various properties. Properties such as ductility, malleability, yield strength, ultimate strength, elasticity, etc. Okay, and how to determine that? That is what we are going to discuss completely. So let us take this is our specimen. Generally, in our specimen, we used to take 2 points, A and B. Okay, let this point be A and let this point be B, and this distance between these 2 points are taken as LG, and LG is nothing but gauge length. Okay, gauge length or original length. And now you might ask me a question, why we are taking these 2 points here? Why can't I take here and this point? Like, why can't I take there? The reason is I'm going to connect this, right? I'm going to connect this end to one side, okay? I'm going to connect this end to one side of the UTM, and I'm going to connect this end, okay, to another side of the UTM. So simply I will be connecting it, okay? So this is what I'm going to do. Okay, I'm going to make it vertical, and then I'm going to place this top side here and this bottom side here. So there is going to be some grip here, okay? We are going to hold it. There is this UTM machine is going to hold this specimen, and due to this grip there is possibility for development of stress here also, okay, development of stress here also. But now I'm going to do this experiment to find out the different material properties such as strength and elasticity, malleability, ductility, etc. So if I take this A point very close to the grip, okay, if I take this A point very close to the grip, then I won't get a proper value. Okay, so proper measurement won't be there. Stress distribution won't be proper. Because of this grip, there will be development of stress, right? So because of that, we are not going to get a proper value. So that is why we need to keep this A point and B point somewhat away from the grip. Okay. So here, this is what grip is. I'm just going to connect this grip here. Okay, right. So what is the procedure? Simple. See, in this specimen, I will be attaching something called as extensometer. Okay, or else I will be attaching strain gauge. Okay, strain gauges. Okay, either electrical, mostly electrical resistance strain gauges only. If you had done your experiment in your college SOM, strength of materials lab, okay, that lab you would have done this mostly. Okay, so either electrical resistance strain gauge will be there or extensometer will be there. And what is the use of that extensometer or strain gauge? It is used for measuring the strain. Okay, it is used for measuring the strain or deformation. Okay, in fact, we will be measuring the deformation only. I will be coming for it later. Okay, so what actually is going to happen? Simple. This end is fixed. Okay, this end is fixed. This end is movable. Okay, I will be having something like I will be having an I will be having what is that exactly called as? I will be having what is that exactly called as? I'm not able to recollect it. Okay, I can say in this manner. Okay, so the controls will be there in my hand. Okay, the controls will be there in my hand. I can use this to move this top side of UTM machine up and like I can move it up or I can move it bottom. Okay, so I'm going to do a tensile test. So what I'm going to do was, this side is fixed. I'm fixing it because this is fixed. Okay, top of this UTM is getting moved. How I am moving it? By using some controls. And by using that control itself, I will get to know how much amount of load I'm applying. See, here I'm moving means here I'm moving means what actually I'm doing. This end is fixed. Okay, this end is fixed. I'm moving the top side. Okay, I'm moving this top side, which means I'm applying some load and I'm increasing the load gradually. Initially, the load applied was 0, and gradually I'm increasing it to a maximum load. Okay, so gradually I'm increasing the load by using this control. Okay, so that is the simple procedure. And how much load I'm applying, okay, how much load I'm applying, and corresponding to that load, how much deflection I'm going to get. Okay, how much load I'm applying, and corresponding to that, how much deflection. Similarly, I can plot this in a graph. Right, like each and every time when I'm applying a load, I will be getting some deflection. Each and every time I'm applying a load, I will be getting some deflection, and I can plot that graph. Okay, so I can plot the graph between load and deflection, and later I can convert this load into stress by dividing it with original area, and similarly I can convert this deflection into strain by dividing it with original length. So this load by original area is called as engineering stress. Okay, it is called as engineering stress. And similarly, this deflection to that of original length is called as engineering strain. See, why I am specifically mentioning the word original, because here we are considering the initial area only. Let us consider the initial area be, initial cross section area be A naught. Okay, every time I will be using that initial area only, and similarly initial length be LG, which is equal to L naught. So every time I will be considering this initial or original length and original area only for calculating engineering stress and engineering strain. But we know very clearly, as I keep on increasing this load, okay, initially if I apply load P1, there will be some deformation. If I apply load P2, there will be some deformation. If I apply load P3, there will be some deformation. So continuously, if load increases from 0 to some maximum value, the length of this member is going to increase. Okay, length won't remain same throughout, right? And similarly, area will decrease because it is a tensile test. So length will continuously increase, area will continuously decrease because of lateral deformation. Okay, but when I'm calculating engineering stresses, I need to use original area only, and when I'm calculating engineering strain, I need to use original length only. But now here comes a term called as true stress and true strain. Okay, true stress, that is sigma t, and similarly true strain, that is epsilon t. True stress are nothing but load applied at that instant. Okay, at that instant, at that time, whatever the load applied, to that of at that instant whatever the area. Okay, suppose I'm applying load P2, and when I'm applying load P2, what is the cross section area? That area has to be included here. If I'm applying load P3, at that instant, what is the cross section area? That has to be taken here. So this is something like load per instantaneous area. Okay, at that time, at that instant, what is the area? Okay, and similarly, true strain is nothing but a change in length to that of that instantaneous length. Instantaneous length means at that instant, whatever the length is, because we know that length continuously changes. So these are called as true stress and true strain, and this load by original area is called as engineering stress, or simply most of the times you will just mention it as stress, or it is also called as nominal stress. Okay, and here this is engineering strain, or simply it is strain or normal strain. Of course I need to include that also, normal stress, normal strain, or else it is simply nominal strain. Okay, now a question comes to most of the students. The question comes, sir, we know that true stress and true strain are different. Okay, like true stress will vary with respect to area, and true strain will also vary with respect to length. But why you are plotting the graph between engineering stress and nominal strain? Why, like engineering stress and engineering strain, why can't you plot it between true stress and true strain? I hope you are understanding my question. My question is, why I need to plot a graph between engineering stress and engineering strain? Why not true stress and true strain? Because we know that true stress and true strain are something which is what I could say, which is more likely, or which seems to be more correct. Okay, correct form of representation of stress and strain. Engineering strain and engineering stresses are not correct form of representation of stress, because we are considering the original area only, but area continuously changes, and we are considering original length only, but length continuously changes. So why you have to represent engineering stress and engineering strain? Why can't you do true stress versus true strain? This question, I hope that few of them would have got. Keep that question in your mind. Hold that question for few more minutes, or maybe, I don't know, if time doesn't permit, then few more class, not few more class, for the next class. Hold that question. I will be giving you an answer. A perfect answer will be given for you. Okay, why we are preferring this, why we are not preferring this, I will be giving you an answer later. Okay, now, so for what we are going to do, simply I'm going to measure load corresponding to delta, and then later I'm dividing with area, I'm dividing with original area for finding out stress, and dividing with original length to finding out strain, and then I'm plotting it in, let me plot it, I'm plotting it in stress strain diagram. And here the stress strains are true stress and true strain, remember that. Sorry, I'm very sorry. I'm very sorry. Here the stress strain are engineering stress and engineering strain. Remember that. We are not doing true stress and true strain. Why we are not doing? I will give the answer later. Okay, is it clear until now? It's difficult to, that is one of the reason, but it is not the complete reason. But it is correct. It is one of the reason. It's one of the reason. It's one of the reason, but it is not the, what I could say, a complete reason. There is one more thing which I will be talking about it later. Any other doubts? Okay, then let me plot the graph and then I will explain all the components. Most probably we will discuss about the properties in the next class only. Okay. Okay, so engineering stress and engineering strain diagram. Okay, so once after finding out P and delta, I am finding out sigma and epsilon. And once if I find the sigma and epsilon, how does the diagram looks? It is something, it will look something like, okay, and okay, somewhat it's fine, I guess. So yeah, it's fine. Okay, so this is O, this is A, and here it is B, and here it is C, here it is D, here it is E, and let it be F. Okay, and this is G. Okay, fine. Okay, so let us see what are the things here. Okay, so this is how a graph looks, and this is most familiar graph for MS, that is mild steel, or most commonly for a ferrous material. Okay, for a ferrous material, right? And this point A, okay, this point A is called as proportionality limit. Okay, proportionality limit. And this point B is called as elastic limit, and this point C is called as upper yield point. Okay, upper yield point. And point D is called as lower yield point, or most commonly we will refer this as yield point. Okay, so we won't refer upper yield point as yield point. Lower yield point we will be generally calling it as yield point. Okay, right. So next, E is the point at which strain hardening start. Okay, so we can say that strain hardening, okay, this hardening starts. Okay, and F is the ultimate point, okay, or else ultimate stress point, or just ultimate point, and G here is fracture point. Okay, fracture point. And this F is also, we can say that it is the point at which necking starts. Okay, necking starts. Now let me divide this. If I divide this graph, I can divide it into two. Basically I can divide it into two. Exactly from the point B, this is elastic region. Okay, this is, see, don't worry, I will be trying to give you each and every what is mean by elastic, all those things I will be trying to give you the details, except a few things. The first thing is, I won't say why there is two yield point, upper yield point and lower yield point. I won't say what is mean by this strain hardening. Okay, why? Because if you already attended material science, is material science over? Material science or metallurgy? Material science or metallurgy class? Yeah, obviously when you are attending material science or metallurgy, my suggestion is to ask your material science faculty why there was a shift from C to D and what is mean by strain hardening, because those two concepts are related to material science. Actually, I don't want to bring that here because that yield point phenomena, C to D, it is called as yield point phenomena. If I start explaining yield point phenomena, it will take some 45 minutes. And strain hardening, again, it will take some 45 minutes, unnecessary wastage of 1.5 hours. So it will be better if you ask, like, anyways, material science faculty will be covering it. Okay, strain hardening and yield point phenomena. That is why it is shifting from C to D. Okay. Okay, so other than that, I will be giving you each and everything which is there in this graph. Okay, so this region is, okay, this remaining region, okay, this remaining region is the plastic, we can say that it is a plastic zone. Okay, the total zone is plastic zone, and this from O to A it is elastic zone. Okay, sorry, O to B it is elastic zone, and from B until G it is plastic zone. Okay. Now again I can divide this further. Okay, again I can divide this further from this point. Okay, that is from this point until E. Okay, from the elastic point until E, that is where the strain hardening start. It is called as plastic flow. Okay, it is called as plastic flow, or it is also called as once again, I forgot the name for it, written somewhere. It is also called as plastic flow, or it is yield zone. Okay, yield zone. Yeah, yield zone. Okay, yield zone or plastic flow. Okay, and this E to F, actually majorly this yield zone will be from D only. Okay, from D only, but this B, C, D, all these points will lie very close to each other. Okay, this B, C, D, all this will be very close to each other. Okay, this E to F. Okay, this E to F is strain hardening region. Okay, strain hardening region, and this F to G is necking. Okay, necking zone or necking region. Okay, so now don't worry much, I will be explaining each and everything properly. Okay, so just be with me until I complete this. Okay, so let me go for, so just wait a moment. So what I did now, initially I just given you all the components of this stress and strain diagram, right? So now I'm going to concentrate only on this elastic zone. Okay, I'm going to concentrate only on this elastic zone. I will complete elastic zone today. Okay, remaining we will be discussing it in the next class, because elastic zone itself will take some 10 minutes. Okay, right. Okay, so if I take elastic zone consists of two parts. Okay, one is linear elastic. Okay, and another one is non-linear elastic. Okay, this is A, let me take this is B, and let me take this is O. Okay, stress and strain. This OA is linear elastic zone, and AB is non-linear. See, what does mean by linear and non-linear? It is pretty straightforward that you could understand that OA is a straight line, right? It's a linear line. But AB it is not, it is some curve. Okay, so you can divide it into two. So this is going to be linear elastic region, and this is going to be non-linear elastic region. Okay, this is going to be non-linear elastic region. And what is the difference between this linear? First of all, what is mean by elastic? Elastic means, if suppose if you are taking a member, and if you are, from the name itself you could see, from the name itself it is saying elastic, right? If you are taking a member and if you are applying a load, okay, if you are applying a load, you are applying some load, it is undergoing some deformation delta. Okay, it's undergoing some deformation delta. Now if you are removing the load, after removing the load, if it comes back to its original position, for example, initially length is changing from Li to Lo, length is increasing. Once if you remove this load, okay, if the length regains back, okay, so if there was a regainment of length again, that is, if it is coming back to its original state itself, then I will call it as elastic without any permanent deformation. That is the correct word to use. Temporary deformation will be there until Until this load P is present, there will be some temporary deformation, but permanent deformation won't be there. So for example, if I'm loading a member from O to this point, okay, I'm loading a member from O to this point, that is stress developed was this much and strain developed was this much, okay. And now if I remove the load, okay, suddenly I'm removing the load, what happens? Again, it will regain, it will go in the same path and it will reach the original position itself. This O indicates the original position. Where stress is 0, strain is also 0. Because when it reaches original position, there is no stress developed, there is no strain also, because there is no deformation, there is no load which is acting. That is what elastic means. What is mean by elastic? From the name itself, it is pretty clear. If I apply a load, it will deform. But if I remove a load, it will come back to original position. There won't be any permanent deformation, right? There won't be any permanent deformation. Only temporary deformation will be there. Okay, so deformation will be completely recovered. Okay. And from the name itself, it is very clear. Until point B only, it's going to be elastic. After point B, it's not going to be elastic, as you could see in this diagram. After point B, it's nowhere elastic, it's going to be plastic. Okay, so until point B only elastic. Now I am concentrating only on this elastic region. Okay, and now why it is linear and non-linear? Because OA is linear line, straight line, and AB is a non-linear line. It is not a straight line, it is a curved line. Okay, so I hope it's clear. Any questions? Until now, no. Okay, now coming back to next thing. There is something called as Hooke's law. Everyone knows this. Most of you in your first centrometrics class, you would have listened to this word Hooke's law, but I taken around 4 hours for introducing this Hooke's law. Okay, so what is mean by this Hooke's law? Hooke's law states that within, it's a very important point, within proportionality limit or within elastic limit. This A is proportionality limit, okay, and this B is elastic limit. So Hooke's law states within proportionality limit, okay, within proportionality limit, stress is directly proportional to strain. You might have a doubt here, sir, why you are saying proportionality limit? We used to study it as elastic limit. The thing here is, you could see here, from O to A, it is linear, but from A to B, it is not linear. See how we are saying this? What actually Hooke's law is saying? Hooke's law is saying nothing. It's very, very simple. If you take y axis and x axis, if you draw a straight line, sorry, so if you draw a straight line, like straight line which passes through, again I'm doing the same mistake. Okay, just consider that it is passing through origin. Okay, so if I take a straight line which is passing through origin, what is the equation of the straight line? Equation of the straight line is nothing but y is equal to mx, where m is the slope, so y is proportional to x. So this is what Hooke's law is saying. It's simple a straight line equation. Here y-axis is stress and x-axis is strain. That is the fact here. Okay, so Hooke's law is nothing. It is a straight line equation. Okay, I'm just giving you a straight line equation. So for removing this proportionality constant, I'm adding a constant which is e. So E into epsilon. So this is what Hooke's law states. And Hooke's law is applied only within proportionality limit, not within elastic limit. Point B is elastic limit, point A is proportionality limit. From A to B, it is non-linear. If it is linear, if it is a straight line, then only I can use this. In a non-linear region, I cannot use this. Okay, so this is an important conceptual question. If suppose they are going to ask a conceptual question from this, for example, they are saying that stress is proportional to strain. It is applied within dash. Then you need to say that it is within proportionality limit. Or else they will say Hooke's law is applied within dash. If option A is proportionality limit, option B is elastic limit, then the correct answer is proportionality limit. Okay, but for solving problems, again we have to do some small, I have to go back there. As I already said that this point A, this point B, this point C, this point C, or this point D, all 4 are lying very close to each other. All 4 are lying very close to each other. So generally what I will do, the sigma A will be taken as sigma B will be taken as sigma D. Okay, sigma C doesn't have much significance. Sigma D is nothing but yield stress. This is elastic. this is proportionality. So all three will be taken as same because almost all are same, right? Almost all are very near to each other. Okay, so that is why when solving problem, okay, when solving problem, we can use this equation within elastic limit also, but that is only for solving problems. But when you are doing concept, when there was a conceptual question, then this is applicable only within proportionality limit. Keep that in mind. Okay, now coming back for it, compare it. This linear elastic region is equal to sigma, and sigma is equal to E into epsilon, and our general straight line equation is what? This is our straight line equation, y is equal to mx. If I compare it, this m is nothing but this E, right? Which is nothing but slope, which is equal to E, which is equal to elasticity, or you can also call it as Young's modulus of elasticity, or what is that another name? Elastic modulus, of course. Elastic modulus, Young's modulus, or elasticity. Okay. So until now, was there any doubt? Until now, was there any doubt? And this E is nothing but a proportionality constant which I'm introducing. And don't worry, I will talk about this E much, okay, more. There are many significance about this E. But now as time, we already reached 12:55, so I don't want to extend this anymore. Okay, so I will talk about this elasticity, all these things later in the next class. So in the next class, I will be completing it. Okay, I will be completing UTM, then I will be starting axial loading, and then we can do some problems. Okay, so from next class, we will start problematic part. So theoretical part is over. So I hope that theoretical part is over. So from next, we will be completely going for problematic part. There won't be any issues. So next, maybe some 1.5 hours or 2 hours, we will discuss this UTM. Later, I will start axial loading. So any doubts until now? Any doubts you can ask me. So I hope that these these videos are available for you, right? It is available for you, so you can watch it and you can take notes, right? So that's it. I will just inform to I'll just inform to Jeremy sir, he can take over. Okay, Devendra Prabhu, thank you. Fine. So that's it. We can end the session. I will, like, anyways, next week I will be coming back.